Malware analysis, a research project. So the team members for this group are Adam Solomon, Ashley Corford, and Amina Lavi. The question you want to ask is, why is malware analysis important? It's imperative that we properly defend information systems against threats. It's necessary to fully understand malware capabilities and behavior as well. Many critical systems remain unpatched and vulnerable. Meanwhile, new vulnerabilities and their exploits are discovered daily. So the first section I'll be discussing is Flare VM setup. So this was the virtual machine that we had to get set up, and here is the process and steps for it. This is the part of the foundation of this setup so that we can carry out the dynamic and static analysis. So first we set up the host. We want to install VMware Workstation on the user's PC. So we download it from VMware's website to get VirtualBox, and we use the default settings during this setup. Then we reboot the host after installation. Next, you want to get the Windows 11 ISO from Microsoft's website. And then we want to create a dedicated folder for VMs on the host's PC. So remember, do not use OneDrive because if you have a shared system, then the malware samples could jump to your actual host, and that's not good. So next, we want to create a virtual machine. So we click on Create New VM, and then we select the typical option, which is recommended. Then we go to our Windows 11 ISO where we stored it, and we select it. Get that, we set our VM name and location, make sure it's local. And for the disk size, we want to have a 60 gigabyte minimum. 100 is ideal. For memory and CPUs, we want 8 gigabytes of RAM at least with 4 cores. And for network adapter, select NAT for the setup phase. Then click Finish, power on the VM. We install Windows 11. We follow the on-screen steps, set up our account, and complete the installation. This will take us to the desktop. Now we have the VMware guest editions. So ensure the right tools are installed, that we're going to need those for later. So at the top of the screen, open the VM dropdown and go to Player, Manage, and Install VMware Tools. Run the setup wizard and reboot. So for security system configurations, we go to Settings, Windows Update, and pause updates. 7 days minimum, more is better. We want to disable Windows Defender, and then we create a snapshot. So this is our clean image so that if anything goes wrong, we can revert back to it. We have a good start off point again. Now you want to install Flare VM. Launch PowerShell as administrator. That's important to be administrator. We set the execution policy with this following command, run the installer, and then put that following command in, which is that installer. We accept the defaults when prompted for paths. There's going to be multiple automatic reboots. If you don't have a pin for your computer, do nothing until it finishes. But if you did set a pin, you're going to need to be there periodically to put in your pin on reboot. The Remnux installation is very similar. You simply download the virtual appliance file, the .ova file, open VirtualBox, import this file, and the settings for installation will be almost identical to Flare VM. Note that this will be much faster than Flare VM, so that is convenient. So Zeus is the malware sample that I worked with, and here are just a few quick results to discuss that. Wireshark, we use this tool. We are showing that the malware repeatedly reaches out to a command and control server. It's disguising these requests as Microsoft update traffic. There are repeated DNS lookups and consistent GET patterns, which are typical of this piece of malware. The HTTP request details for a specific packet demonstrate that the malware is sending a false Microsoft update GET request to exfiltrate and retrieve encrypted data. The URL path is designed to blend into the rest of the Windows traffic, making it harder to find. Lastly, Ghidra. Using this tool, we saw the entry point of the malware and its packed loader stub. The control flow here is shown to be purposely obfuscated. We see that the unresolved jump table and their indirect calls to function confirm that the real payload is unpacked dynamically in memory. Next, we're going to discuss the virtual network.
Hi, so I'll be going over the virtual network. Here we can see how we had to set up a virtual network adapter so that we'd have a secure and safe environment to work in, and so both of our virtual machines could communicate. So for this part of it, we set up a host-only adapter, and we set a specifically new subnet compared to like with the 10.0.0.1 subnet. In this case, we also set it up as a DHCP server so that they could automatically get IP addresses from it. Next slide, please. Here's an example of part of the setup that had to be done. On Remnux, we encountered a problem where after reboots, it would lose its IP address. So we created this brief bash script to renew the IP. And here we can see inetsim setup. Inetsim is what we use to simulate network traffic so that the malware thinks it really is communicating with the internet. In this case, some of it had to be manually set up with DNS so that they could do lookups. Next slide, please. Here's an example of our setup. In this case, we have both systems connected with each other, with the adapter having its own gateway address, its DHCP server address, and then each having its own IP address. Again, we made sure also to have it on a specific subnet with the 10.0.0 just to differentiate it from our own network so there's no confusion and to ensure it's a much safer overall procedure. Next slide, please. And here's an example of some of the work on Flare VM that had to be done to set up DNS. We just had to manually configure it so that our Remnux device was our DNS server. And at the bottom, you can see an example of what it looks like when you make a request when this is working. So none of these computers are connected to the internet. They're only connected to each other. In this case, however, if you look up any website, any domain, it will give you this fake landing page, but the malware will think it is actively working. Next slide, please. Here's an example also of some of the safety procedures done. So in this case, the top is from my own personal computer where I was sending a ping to the Remnux virtual machine. For this, there was network, it was able to communicate to it, which is also through the hypervisor, which makes it more secure. And at the bottom, we can see it. I'm trying to ping my own personal computer and it cannot reach it. So in this case, it's a safe and secure environment if our own personal computer can communicate with the VM, but the VM cannot communicate with us. That shows it's a safe environment. Next slide, please. So I'll also briefly go over WannaCry, which was my malware sample. Next slide, please. Here we see a brief overview of some of the information done. Here we're using the tool CFF Explorer to get information. We can see it's compiled with Microsoft Visual C++ 6.0 and get other useful information. Next slide, please. Another useful tool was Detected Easy, which showed this malware was highly compacted, very obfuscated, and gives us other useful information about how it was set up. Next slide, please. And here's just some examples of the strings that were extracted, which give us useful information. So some of these, such as exe files and here whatnot, are set up as part of persistent measures for WannaCry. Next slide, please. And finally, here's an example of what it looks like when WannaCry fully detonates and you have a very bad day. And this shows kind of part of our dynamic analysis step. And next slide. And now moving on to Ashley.
So I'll be covering Redline Stealer. This is the initial static triage using Detected Easy. This identifies the sample as a 32-bit PE file, which tells me it's a .NET executable. It's built in the .NET framework and also flags obfuscation with bad naming, which is common in .NET malware to hide class and function names. Next, moving on to Floss. This slide shows the Floss output for the sample. Floss immediately warns that .NET specific string extraction isn't supported. It also can't deobfuscate .NET strings because of our malware is a .NET binary. Floss is only able to pull very basic static strings. That's why the execution finishes quickly and doesn't produce meaningful results. The next slide shows that the full Floss output for the sample, Floss correctly identifies it as a .NET binary, but since Floss does not support .NET string decoding, most of the meaningful strings are missing. It was only able to extract about 1,600 static strings, and almost all of them are just noise, which is typical when a .NET sample is obfuscated. Moving on to the next slide. This slide shows the section headers of the sample. What stands out is how small the text section is, which is unusually tiny for a functional malware payload. A small text section usually means that there isn't much executable logic inside the file, combined with almost no imports that the .NET metadata we saw earlier. This reinforces the idea that this sample is a stub or a loader shell and not a full malware payload. Moving on to the Ghidra slide. When I opened the file, Ghidra immediately treated it as a .NET managed code, which matches everything we saw earlier. The decompiler shows that the entry point calling core xmain, which is the standard .NET runtime launcher. Moving on to DNSpy. In DNSpy, you can see the full PE structure, including the DOS header, file header, text section, resources, and all the .NET metadata streams. But the most important thing, DNSpy doesn't show any real namespaces, classes, or methods beyond the bare minimum. There's no malicious logic here, no functions, and no program flow to analyze. The assembly essentially contains only headers and metadata with no actual code. Next slide shows that Process Explorer is running during detonation attempts. What's important here is that nothing suspicious ever happens in the process tree. When I executed the malware, there was no new processes, no injected thread, no child processes being created. The system stayed completely idle, which is not what you would expect from an active piece of malware. One major challenge we ran into was the malware refusing to fully detonate. Every time it was ran, the executable opened briefly and then terminated. To rule out environmental blocks, we adjusted group policy settings and created folder-based exclusions so that Windows Defender wouldn't interfere. Even after doing all of that, the sample still wouldn't run long enough for meaningful dynamic data. The second big challenge came from using Redline. Every time I attempted to collect runtime data, Redline returned almost nothing, no suspicious processes, no network connections, and no registry modifications. At first, we thought this meant something was wrong with the setup, but after more research into Redline's limitations, I realized this wasn't a tool issue, it was the malware itself. The sample turned into be a stub, meaning it's only a loader shell that requires another file or payload to complete execution. Without that secondary component, the stub simply opens and exits, which explains the immediate shutdown and lack of dynamic indicators. From this project, we learned how important a repeatable workflow is when dealing with malware. We learned that failure to detonate can still be meaningful and lead to strong static conclusions. The biggest takeaway was how to systematically rule out environmental issues versus sample-specific issues, and how to communicate findings clearly even when a sample doesn't behave as expected. So in conclusion, the next steps are expanding the workflow for analyzing Linux binaries would be beneficial in order to define a robust process for malware analysis on the Linux operating system. Additionally, creating more standardized processes for deobfuscating binaries will be crucial to better understand the more granular details of a particular sample. And we want to give a special thanks to Aswin for his guidance throughout this term.